Hello students, I am Sumit Kolkar, working as Assistant Professor in Civil Engineering Department, Sanjeevani College of Engineering, Kopargaon. Now, in today's video lecture, we are going to discuss about a new topic, that is flow through the pipe. In that, we are going to discuss about the definition of the pipe, next the definition of the frictional resistance, and what happens when the fluid flows through the pipe. Now, the definition of the pipe. A pipe is a closed conduit which is used to carry the fluid under pressure from one place to the another place. This is the simple definition of the pipe. Pipe is used to carry the fluid under pressure from one place to the another place. But when the fluid flows through the pipe, what happens with its resistance? And that we are going to discuss in the frictional resistance topic. Now, when the fluid flows through the pipe, the frictional resistance takes place to the motion of the fluid. That frictional resistance, it is due to the friction between the molecules of the fluid themselves, or due to the friction between the molecules of the fluid and the wall of the pipe. Due to that frictional resistance, the energy loss takes place along the direction of the flow. That energy loss is in the form of decrement into the pressure along the direction of the flow, and that decrement into the pressure along the direction of flow is known as head loss. Now, the Darcy's-Weisbach equation, it is the name of scientist Darcy's-Weisbach, it is the name of scientist, he had given the equation for the head loss. Head loss is given by HF is equal to FLV square upon 2GD, where HF is nothing but it's a head loss along the direction of the flow, F is nothing but it's a friction factor, L, it is the length of the pipe between two sections, section 1 and section 2, V, it is the velocity of the fluid through the pipe, D is nothing but it's a diameter of the pipe, and G is constant acceleration due to gravity. Now, before deriving the equation for the head loss, first of all, we will discuss on Froude's experiment. Remember that Froude, it is the name of the scientist. He has conducted the series of the experiment to investigate the frictional resistance offered by the flowing fluid along the direction of the flow. From the results of this experiment, following conclusion has been made by the Froude. The first conclusion was the frictional resistance. The frictional resistance varies approximately with the square of velocity. The frictional resistance F, it varies with the square of the velocity. And the second conclusion which he has made is the frictional resistance varies with the nature of the surface of the pipe. Therefore, from the results of Froude experiment, the total frictional resistance is given by this formula. F is equal to F dash into A into V raised to N, where capital F is nothing but it's a total frictional resistance. This total frictional resistance it offers when the fluid flows through the closed passage. F dash is equal to the frictional resistance per unit area of a given surface at a unit velocity. It's a frictional resistance offered over the unit area for a unit velocity, F dash. A is equal to the area of weighted surface. It is the area of weighted surface, or we can say it as the area of contact also. This A is given by P into L, where P is nothing but the perimeter, and all of you know that how to calculate the value of perimeter. It is equal to pi into D in terms of diameter, or it is equal to 2 pi r in terms of radius. L is equal to the length of the pipe, whereas V is equal to the velocity through the pipe. And as per the conclusion number 1, the frictional resistance varies approximately with the square of the velocity. Therefore, the value of N is equal to 2. Therefore, we have the total frictional resistance which is given by the Froude is equal to F is F dash into A into V square. You have to remember this equation because this equation we will require to solve the Next problem. Now, all of you know that when the fluid flows through the pipe, it offers a frictional resistance along the direction of the pipe, along the direction of the flow. That resistance, it is in term of losses. So there are different type of the energy losses. The first one is the major loss and the second one is the minor loss. Remember that major loss, it takes place due to the friction only. When the fluid flows from one point to the another point, then due to the friction between the molecules of the fluid themselves or due to the friction between the molecules of the fluid and the wall of the pipe, the frictional resistance takes place, and that loss is the major loss, and second loss is the minor loss. Remember that minor loss, it takes place due to the change in velocity. The change in velocity, it may be in terms of its magnitude or may be in terms of its direction. Due to the change in velocity, the minor losses takes place. You have to remember it. There are different type of the minor loss. The first one, due to the sudden expansion, due to the sudden contraction, if a bend is provided into the pipe, due to the pipe fitting which are installed onto the pipe, and due to the obstruction in pipe. Those losses, it comes under the minor losses, and the major loss, it is due to the friction only. Now in the next slide we are going to derive the major loss, means it is the head loss. Now derivation of loss due to the head of friction, means it is also known as friction loss. Now from the figure you have to consider a straight horizontal pipe of same cross-sectional area throughout its length. As the cross-sectional area of the pipe is same, the velocity will remain constant. There will be no change in the velocity. Now onto the pipe you have to concentrate on section 1 and section 2, and that section 1 and section 2 has the length is equal to L. Remember that this is the horizontal circular pipe which has a constant cross-sectional area and a constant velocity. As there is no change in the area, the velocity will remain as it is. Now from the figure, let L is nothing but the length of the pipe between section 1 and section 2. Small d is the diameter of the pipe. It will remain as it is. It is a constant value. Small f is the value of friction factor which depends upon the roughness of the pipe. H1 is the loss of head due to the friction. Not H1, it is HF. It is the loss of head due to the friction. When the fluid flows from section 1 to the section 2, there must be decrement into the pressure due to the frictional resistance. And that loss is nothing but the head loss. P1 is the intensity of pressure at section 1, small p1. V1 is the velocity at section 1. In the same manner, we have P2 and V2 are the corresponding values of intensity of pressure and the velocity at section 2. Now we are going to apply the Bernoulli's equation for a real fluid at section 1 and 2. Remember that for a real fluid we are applying the Bernoulli's equation, means for the real fluid when it flows from section 1 to the section 2, there always a head loss, and that head loss we have to add onto the second section because it takes place along the direction of the flow. Now we will apply the Bernoulli's equation section 1 and at section 2. At section 1, the Bernoulli's equation is P1 upon gamma plus V1 square upon 2G plus Z1, which is equal to P2 upon gamma plus V2 square upon 2G plus Z2 plus HF. Remember that HF is nothing but it's a loss of head along the direction of flow. And rho into G, all of you know that it is the value of specific weight which is denoted by the letter gamma. As our pipe is horizontal, therefore the value of Z1 and Z2 are 0. The datum will remain constant. As our pipe has the same cross-sectional area throughout its length, Therefore, there will be no change in the velocity. Velocity v1 and v2 will remain same. Therefore, if I rearrange the equation, if I put the value of z1 and z2, v1 and v2, we will get the following equation. That following equation is hf is equal to p1 upon gamma, rho into g is nothing but gamma, minus p2 upon gamma. This is the equation number 1. hf is equal to p1 upon gamma minus p2 upon gamma. It shows that the loss of head along the direction of the flow. The negative sign of p2 upon gamma, the negative sign upon gamma, it indicates that the pressure decreases along the direction of flow due to the frictional resistance only. Now, as the velocity is constant throughout this section, there will be no acceleration or no retardation takes place. Therefore, the sum of the forces in the direction of motion must be equal to 0. Now, this particular fluid element between section 1 and section 2, it is subjected to forces. The first force is pressure force in the direction of motion, and the second force is the frictional resistance which is given by the Froude experiment. The Froude experiment we have already discussed in the previous slide. Therefore, we will make the summation of all the forces which is acting along the direction of the flow. Now, the first force is P1 into A. It is the value of pressure force at section 1. It has a positive sign because it is acting along the direction of the flow. It has a positive sign because it is acting along the direction of flow. This is the direction of the flow. Next one, P2 into A. It has a negative sign because it is acting against the direction of flow. If I make some mathematical simplification, if I make all the terms to one side, then P2 into A will become negative. And the second force is frictional resistance force. Again, it acts against the direction of the flow. Now, all of you know that if I make the mathematical simplification, A is common to all. Therefore, if I bring P2 into A onto left side, it will become P1 minus P2 into A, which is equal to the frictional resistance. And all of you know that how to write down the equation of frictional resistance by Froude's experiment. It is F dash into A into V square. Therefore, we have the equation P1 minus 2 into A, which is equal to F dash into PL into V square. Remember that A is nothing but it's a contact area, and the contact area it is given by P into L. Whereas P is nothing but it's a perimeter of the pipe, L is nothing but it's a length of the pipe. The value of perimeter, weighted perimeter, is given by pi into d, which is, or in terms of radius, it is 2 pi r. If I put the value of perimeter and if I make the mathematical simplification, we have the equation P1 minus P2, which is equal to F dash into P by A into L into V square. Remember that P by A, it is the inverse of hydraulic radius. P by A is the inverse of hydraulic radius. It means that if I consider A by P, it will become the hydraulic radius, and hydraulic radius is denoted by the letter R. Now, if I put the value of A upon P in the previous equation, in this equation, we have P1 minus P2, which is equal to F dash into 1 upon hydraulic radius, which is denoted by the letter R, into LV square. If I divide the entire equation by gamma, this is gamma, then we have P1 minus P2 upon gamma, which is equal to F dash into 1 by R into LV square whole upon gamma. And all of you know that P1 minus P2 upon gamma is equal to head loss. Therefore, head loss will become F dash into 1 upon R LV square upon gamma. Now we will put the value of R from this equation. We have R is equal to A upon P. Therefore, the value of A is pi by 4 into D square. The value of P, it's a perimeter, pi into D. Then after cancelling pi, we have the remaining equation D by 4. Now you put the value of R into this equation, we have this equation. And after making some mathematical simplification arrangement, HF will become 4 FLV square upon gamma D. Remember that, therefore, we have the equation for F dash upon gamma is nothing but F upon 2G. This equation is based on the experimental result which have performed by the Freud. Therefore, we have the head loss is equal to FLV square upon 2GD. Or in terms of discharge, we have the head loss FLQ square upon 12.1 into D raised to 5. The head loss in term of discharge we have calculated from the continuity equation. We have the continuity equation Q is equal to A into V. We have the continuity equation Q is equal to A into V. Therefore, we will put the value of V from the continuity equation, and that value is Q by A. If I put the value of area again, it is pi by 4 into D square. If I put the value of G, we will have this equation HF is equal to FLQ square upon 12.1 into D raised to 5. This is the value of head loss in term of discharge. You have to remember all these two equations for the future use. HF is equal to FLV square upon 2GD. It is the Darcy's-Weisbach equation. It is the head loss when the fluid flows from point 1 to the point 2. And this is also the head loss, but it is in term of discharge. Now, our next topic is minor losses. As discussed earlier, the minor losses takes place due to the change in velocity of the flowing fluid. The change in velocity, it may be in magnitude or it may be in direction. If there is change in magnitude in the velocity, or if there is change in the direction of velocity, then the minor losses takes place. There are different type of the minor loss. The first minor loss is head loss at the entrance of the pipe. When the fluid enters through the pipe, at the entrance the minor loss takes place. That loss is given by 0.5 into V square upon 2G, where V is the velocity of the liquid in the pipe. At the entrance of the pipe, the minor loss is given by 0.5 into V square upon 2G. Now at the exit of the pipe, again the minor loss takes place, and that value is V square upon 2G. Again, V is the velocity of the liquid at the outlet of the pipe. The minor loss, it also takes place due to the bend in the pipe. That bend in the pipe, that minor loss due to the bend in the pipe is given by K into V square upon 2G, where V is the velocity of the flow, K is the coefficient of the bend which depends on the angle of bend, radius of curvature of the bend, and the diameter of the pipe. Remember that the head loss due to the bend in the pipe is given by K into V square upon 2G. The value of K, it depends upon the coefficient of bend which depends on the angle of bend, the radius of curvature of the bend, and the diameter of the pipe. This is very important one. And the next one, head loss due to the pipe fitting. If number of pipe fittings are installed onto the pipe, due to that also the minor loss takes place. It is given by k into v square upon 2g. Again, the value of k, it depends upon the coefficient of pipe fitting. Next, the minor loss, it also takes place due to the sudden enlargement also. The minor loss also takes place due to the sudden contraction also. And that derivation for sudden enlargement and sudden contraction we are going to discuss in the next slide. Now, minor energy loss due to sudden expansion. Now, what does it mean, sudden expansion? It occurs when the pipe of certain diameter suddenly expands to large diameter. When the pipe of certain diameter, suppose this diameter, it suddenly expands to large diameter. Now this particular smaller diameter pipe, it get expand to larger diameter pipe, therefore there will be occur a minor loss. This particular minor loss for due to the sudden expansion can be determined by applying the impulse momentum equation along with the Bernoulli's equation. Now why we have to apply the impulse momentum equation along with the Bernoulli's equation? Now at section, we will concentrate on section 1 and section 2. At section 1, the diameter of pipe is less as compared to 2. As the diameter of the pipe is less, means the velocity will be more at section 1, and here it is the velocity will be less as compared to 1. So when the fluid flows from section 1 to section 2, there will be the momentum, change in the momentum of the fluid. And that change in momentum of the fluid is nothing but it is equal to the mass of the fluid into the velocity of the fluid. That equation we are going to apply to derive the equation for sudden expansion. And again we are going to apply the Bernoulli's equation. Now from the figure we will concentrate on section 1 and section 2. At section 1 we have the area equal to A1, intensity of pressure P1, velocity at section 1 it is V1. At section 2 we have the area A2, intensity of pressure P2 and the velocity V2. Now we will apply the Bernoulli's equation for the real fluid at a section 1 and 2. What does it mean for the real fluid? Now as the fluid is real, means the head loss takes place onto the section 2 side or onto the downstream side. Now at section 1 we have the Bernoulli's equation P1 upon gamma plus V1 square upon 2g plus Z1, which is equal to P2 upon gamma plus V2 square upon 2g plus Z2 plus He. Remember that He is nothing but it's a head loss due to the sudden expansion. Now as our pipe is horizontal one, we can consider any horizontal line as a datum line. Therefore, our value of Z1 and Z2 are equal. So they will get cancelled. Now, if I calculate the value of He after putting the value of Z1 and Z2 equal to 0, we have equation number 1. Equation number 1 gives He is equal to P1 minus P2 upon gamma. As discussed earlier, rho into g is nothing but gamma plus V1 square minus V2 square upon 2g. Now what does it mean? If you concentrate on equation number 1, we have the minus sign for P2 upon gamma. The minus sign for the P2 upon gamma, it indicates that the decrement into the pressure along the direction of the flow. Now at section 2, we have the velocity less than at section 1, therefore we have the minus sign at section 2. Therefore this is the minus V2 square, it indicates that the less velocity as compared to the first one. This is the equation number 1 for the head loss due to sudden expansion. Now from the figure we will consider a control volume of liquid between section 1 and section 2. Now this is the control volume of liquid between section 1 and section 2. Resolving the forces acting onto the liquid inside the control volume, we get summation of f of x. Remember that fx is nothing but it is the sum of all the external forces along the direction of the flow, along the one dimensional only. So the first force is P1 into A1, which is acting along the direction of the flow, therefore we have the plus sign, minus P2 into A2 plus P dash into A2 minus A1. Now all of you know what is P1 A1 minus P2 A2, but we don't know what is P dash A2 minus A1. Now remember that P dash is nothing but it's a intensity of pressure of the liquid ADs onto the area A2 minus A1. It is the P dash is nothing but it is the intensity of the pressure of the liquid ADs onto the area A2 minus A1. Because all of you know that area at section 2 is greater than at section 1, therefore we have the minus sign for A1. Now experimental result shows that the value of P dash is equal to P1. You have to remember this. The experimental result shows that we have P dash is equal to P1. Now if I put the value of P dash equal to P1 and if I solve this mathematical equation, we have the following equation: fx is equal to P1 minus P2 into A2. We have this equation after putting the value of P dash equal to P1. This value, it depends upon the experimental result. Now, as discussed in earlier slide, to derive the energy loss due to the sudden expansion, we have to apply the Bernoulli's equation as well as the impulse momentum theorem. Now, we are going to calculate the value of momentum of the liquid at section 1. Therefore, that value is momentum of liquid per second. Remember that this value, it is per second. The momentum of liquid per second at section 1 is equal to, actually momentum is given by mass into velocity. Momentum is given by mass into velocity. Now mass is nothing but, as discussed in the unit number 3rd, the mass for the flowing fluid is given by rho into A into V. You have to remember this. The mass of the flowing fluid is given by rho into A into V. Now we are applying that at equation 1. Therefore, our equation becomes rho into A1 into V1 into velocity, means it will become rho A1 V1 square. The momentum is nothing but it is mass into velocity. All of you know the mass flow rate, it is rho AV. Now we are applying it at section 1, means it will become rho A1 V1 square. Similarly, the momentum of liquid at section 2 is given by rho A2 V2 square. Therefore, the change of momentum of liquid per second is given by, now we will subtract this value from this one. We have rho A2 V2 square minus rho A1 V1 square. Now after that we have the equation which is equal to, by Newton's second law of motion, we will have net force. By Newton's second law of motion, we have the net force is equal to rate of change of momentum. Now the net force is nothing but it is the summation of f of x, and the rate of change of momentum is nothing but rho A2 V2 square minus V1 V2. And this summation of f of x, as already calculated, we have this equation. After calculation of f of x, we have P1 minus P2 upon gamma, which is equal to V2 square minus V1 V2 upon G. Now, after solving the equation, we have HE, it's a minor loss, is given by V1 minus V2 square upon 2G. Remember that this is the value of minor loss due to the sudden expansion. Now this value is obtained by putting all the values of P1 minus P2 upon gamma and V2 square minus V1 upon V2 square. Now this is the final equation for the minor loss due to the sudden expansion. You have to remember this equation. This equation will be required for solving the numericals. The minor loss due to the sudden expansion is given by V1 minus V2 square upon 2g. Again we have the minus sign over here for the second section, velocity at second section, because as the area increases the velocity decreases. Now our next topic is minor energy loss due to the sudden contraction. Now remember that the sudden contraction, it is the reverse case of sudden expansion. In case of sudden contraction, the pipe of certain diameter suddenly contract to a small diameter. It is the reverse case of sudden expansion. Now to derive the equation for minor loss due to the sudden contraction, we are not going to apply the impulse momentum equation, because from the diagram you can observe that at section 1 and at section 2 the streamlines are converging over here. The streamlines are continuously converging over here to enter into the second pipe. The streamlines are entering from section 1 to section 2. Therefore they start converging from some distance from the junction. As they are converging from this point, there will be the continuous changing into the pressure. Therefore it is not possible to apply the impulse momentum equation, but just onto the downstream side of the junction of two pipe we have a smaller cross sectional area of the jet. Now this is the smallest cross sectional area of the jet, and that smallest cross sectional area of the jet is known as vena contracta. As discussed in the earlier slide also, or earlier video lectures also, vena contracta, it has a smaller diameter and the maximum velocity. Now this point C is the section of vena contracta. Now if you observe from section C to section 2, the velocity at section C is very high, and at section 2 it again becomes the uniform. Means it resembles like the case of sudden expansion. In case of sudden expansion also, a velocity is maximum at section 1 and velocity will be minimum at section 2. The same case is happening over here. At section C we have the smallest diameter, means the velocity will be maximum, and at section 2 we have the less velocity as compared to C. Now from the figure we have A1 is equal to area at section 1, P1 is the intensity of pressure at section 1, V1 is the velocity at section 1. This is all about the section 1. Now in the same manner we have A2, P2, V2 are the area, pressure and the velocity at section 2, and AC, PC and VC are the corresponding values of area, pressure and velocity at section C. Now as discussed earlier, it is the case of sudden expansion from C to 2. We have the equation of sudden expansion, and that sudden expansion loss due to the sudden expansion between section C and 2 is given by Vc minus V2 bracket square whole upon 2j, because at Vc we have the maximum velocity, at V2 we have the minimum velocity, therefore it will be the case of sudden expansion, and whole square upon 2g. Now if I make some mathematical simplification, we have the common term V2 square upon 2g in this manner. So the remaining equation will become Hc is equal to V2 square upon 2g into Vc upon V2 minus 1. It's a mathematical simplification. Now from this equation we are going to determine the value of Vc upon V2 by continuity equation. We have to put the value of Vc upon V2 from the continuity equation, and we have the continuity equation Q is equal to AC into Vc, which is equal to A2 into V2. Remember that we are going to concentrate on section C and section 2 only. We are not going to concentrate on section 1. At section C and section 2, we have the continuity equation AC VC is equal to A2 V2. Therefore, we have VC upon V2 is equal to A2 upon AC. Therefore, AC upon A2 will become 1 upon CC. That value we are going to put into this equation. Remember that in this equation we have head loss is equal to V2 square upon 2G into Vc upon V2 minus 1 into bracket square. We are going to put the value of Vc upon V2 from the continuity equation, and that value is 1 upon Cc. Now after putting the value of 1 upon Cc into this equation, we have V square upon 2G into 1 upon Cc minus 1 bracket square. Now this particular term 1 upon Cc minus 1 bracket square, it is the term of K. It's a constant value, and the value of K, it lies between 0.5 to 0.7. So we can consider any value of K for the sudden contraction, and that value is 0.5 to 0.7. We can consider 0.65 also, we can consider 0.6 also. Depending upon that, we have the sudden expression for the sudden contraction. Hc is equal to K into V2 square upon 2G. Now this is all about the flow through the pipe and the definition of pipe, frictional resistance, the losses takes place in the pipe. Thank you.